So we're happy to have with us Jitin Rai Khanna, who's the Global Sales Director for HIUV, real leader in encapsulation solutions, and he will talk about their multi-scenario offers for N-type cell technology. Jitin, the floor is yours.
Thank you very, very much, Michael.
Jitin, good to go. So just tell her always when she should move on.
Yes, please.
Next slide, Uday. Just
a second, please. Okay. So good afternoon, everyone. It's good to be here with you all today. My name is Jitin Rai Khanna, and I am the Global Sales Director for HIUV. I'm overseeing the expansion and sales for the company. I've been working in the solar material industry for nearly 2 decades, gaining deep insights into market dynamics, technology advancements. We'll go on the next one, please.
Jitin, can you see the presentation?
Yes, please. Okay. So while many in the solar industry do recognize HIUV, which is now amongst the top 3 encapsulant makers in the world currently, nevertheless, I would just like to take a minute to update all about HIUV's journey, achievements, and exciting plans for the future. So HIUV is a stock-listed company with a robust global footprint with 120 gigawatt of capacity, and we do hold many honors and patents both in China and US. The next one, please. We currently have 6 facilities, 5 in China, 1 in Vietnam, and in 2024, we are taking a significant step towards becoming a global leader in the encapsulant industry, as we've already signed a new joint venture with H.B. Fuller in US and another one upcoming in Turkey. Additionally, in 2025, we are excited to announce the establishment of a 5 gigawatt factory in India, which will expand to 15 gigawatt in its next phase, marking another milestone in our global expansion journey. Next, please. So HIUV began its journey in 2005, and we entered the solar industry in 2009 with the manufacturing of EVA for solar modules. 2012, we pioneered the anti-PID EVA, revolutionizing the module performance. 2014, we developed the pre-cross-linked white EVA, enhancing the module power by 0.8 to 1.5%. 2018, we launched the co-extruded POE, setting new standards in innovation and efficiency. So today, HIUV continues to grow alongside the solar industry's evolution, driving advancements in encapsulant technology. Next one, please. So this was a bit about HIUV. Now we will just dive into the tech that we offer, especially for glass-to-glass N-type, which is now the mainstream product and has maximum share of production. So we'll also touch base on dual glass and dual EVA, along with the zero bus bar interconnection technology and lightweight dual glass single-side white EVA films, which improve efficiency. Next one, please. So this is, this is our EPE film, which is now the TOPCon's first choice in the encapsulation industry, for encapsulation. The advantages are that it has been upgraded. It's suitable for all types of TOPCon cell encapsulation requirements. The formulation of encapsulant additives are optimized to enhance the product's anti-PID polarization performance. The POE layer in the EPE structure is strengthened to effectively prevent lamination bubbles. During the mix sealing process of EPE with EVA, there's no additional padding required on the edges, hence achieving a lamination yield of up to 100%. This is very much in mass production now, and the product fully meets the client's stringent requirements in terms of reliability, which is confirmed by the customer's internal validation data. The product also performs well in terms of resistance to PID 192 and thermal humidity performance, damp heat 2000. Next one, please. So HIUV would like to introduce you this new product that we have just launched. We call it the P507S. Now, this is this function of this is fully matching the performance index of a POE film. It's significantly reducing the amount of POE resin and producing lower gram weight co-extrusion film. So these features address the needs of users in seeking alternates to pure POE film, which leads to reducing the cost and improving production efficiency, giving users cost advantage and production flexibility. Next one, please. So now this one and the next couple of slides, I will just give some insight on the dual EVA in glass to glass. So we have two variants. One is a transparent film EVA and the other one is the white film. Now the advantage that we have is its higher moisture barrier effect. It is ultra low acid value and of course superior anti-PID effect. Next one, please. So low acid is a very, very critical requirement now in the EVA for encapsulation. So it gives high resistance to PID. It enhances the reliability and stability of photovoltaic modules by effectively capturing the absorbed ions and blocking the ion penetration, thereby minimizing solar cell power degradation and extending the service life of the modules. The metal ions, such as the sodium and potassium, can be captured, absorbed through cation exchange complexation to reduce the influence of impurity ions on solar cell power. By reacting with matrix resin to form a dense network structure, it can effectively block the penetration of sodium, potassium, and other metal ions and play a very effective anti-PID role. Next one, please. So, this is giving you some insight with the EL images when we compare the low acid EVA with the regular. When we do the HAST, the highly accelerated stress testing for 48 and 96 hours, we can clearly see the low acid EVA, when used, will have minimal or no cell degradation with uniform brightness across cells. This demonstrates effective protection against moisture ingress and corrosion, preserving the self-performance due to its strong anti-corrosion properties. But in the case of the regular EVA, if used, will lead to degradation in solar cells, including dark areas, which we can see in the EL image. It's caused by acid reaction in the humid environment. Signs of microcracks, discoloration, bus bar corrosion, and delamination will be visible, leading to significant performance loss over time. So again, these EL images will clearly illustrate how low acid EVA ensures superior durability and stability compared to regular EVA under extreme stress conditions. Next one, please. So I'm going to talk a bit about the performance enhancement mechanisms that we use. We achieve increased moisture resistance by adding hygroscopic additives and using special cross-linking processes to enhance the film's moisture resistance, reducing the risk of moisture ingress into the cell module and lowering the degradation. So we add ion trappers, and this forms a protective or stabilizing layer on the cell surface, blocking the diffusion of metal impurity ions, thus reducing their detrimental impact on cell performance, thereby improving the stability and reliability of the module. We introduce the anti-cation additives into the film, which enhances the film's ability to absorb or repel cations, thereby improving its cation barrier properties. Now, lowering the acetic acid content in EVA, it reduces the amount of acidic substance in the film, thus reducing the likelihood of self-surface corrosion. Acidic substances, we all know, can accelerate the metal oxidation and corrosion by reducing their content. The risk of corrosion on the cell surface is minimized, thereby enhancing the module's stability and durability. We all know cell metallization usually consists of aluminium, copper, which may be subject to electrochemical corrosion. But when we use EVA with low acetic acid content, it can minimize the contact between the acidic substance in the film and metals, thus reducing the risk of electrochemical corrosion and extending the module's lifespan. Next one, please. So this slide and the next two ones, I will just share how the improved low acetic EVA performs in comparison to the regular EVA in TOPCon with LiCo, showing different contrasting combinations. So these EL images will confirm that TOPCon with LiCo has better reliability performance. Next one, please. So this is a dual glass with a dual EVA combination of a PID study for TOPCon cells. Now, during the testing, we took the cells in dual glass with dual EVA, and we stored that in a dark room for 2, 6, and 12 hours with EL imaging showing improved visibility over time, suggesting a self-healing effect. After PID testing, the cells were exposed to sunlight for 8 hours, and the EL imaging revealed all cells lighting up, indicating recovery from PID degradation. So these results and images clearly demonstrate the protective and restorative benefits of dual glass, dual EVA for TOPCon cells, ensuring better performance and durability under stress. Next one, please. So this is a similar one we did for the LiCo, as LiCo is now picking up in the market. The same thing we did with LiCo with dual glass and dual EVA, which we stored in a dark room after unpacking and underwent an EL testing for 2, 6, and 12 hours, which again showed significant improvement in EL visibility over time. We did the PID testing, and the cells were exposed to sunlight for 4 hours, and EL imaging showed all cells lighting up, indicating recovery from degradation. So these results highlight the resilience and self-healing properties of TOPCon LiCo cells in dual glass, dual EVA packaging. Next one, please. So this is another study which we did for, again, dual glass, dual EVA for the power. Now, based on the same formulation of dual glass, dual EVA, PID 192, LiCo cells are more light sensitive compared to non-LiCo cells, with power recovery easier under light. The cooling time after unpacking the dual glass, dual EVA significantly affects the test results as showed in this graph. Next one, please. So in this combination of, we did a combination of a single glass with dual EVA and with the HAST testing study. So in this single glass component using EVA plus white EVA combination. So this time we used the white EVA. We tested the TOPCon LiCo from 2 manufacturers, A and B. Now the findings are quite interesting. The HAST testing revealed that different manufacturers' TOPCon LiCo cells showed significant differences in moisture response, with manufacturer A showing edge corrosion and B showing increased resistance in overall darker EL. So compared to manufacturer A, manufacturer B's cells showed greater power degradation. Next one, please. So that was a bit about the EVA tests and the low acetic EVA's benefit. And I'm just going to touch a bit base on the module interconnection technology from multi-bus bar to zero bus bar.
2 minutes,
So,
please. 2 minutes. Yeah. 2 more minutes.
yes, please. Yes, please.
No, 2 minutes left. You have 2 more minutes actually for your presentation.
All right, Michael. Yeah. So the module interconnect, we just two slides left. The development of module interconnection technology is always focused on high efficiency, low silver usage, fine welding ribbon thin films. Current market approaches to zero bus bar technology vary, summarizing the following four. So the key technologies are light thermal, curable adhesive, fixed welding tape. The film used is skin. Contact method is lamination forming. Then the other one is a cell phase film, where again the film technology is skin. Contact method is heating plate plus lamination forming. Welding plus adhesive fixed welding tape. Film technology is conventional film, and the contact method is normal lamination. The last one is the welding tape film, where the carrying film is used, and lamination forming alloy. Next one, please. So this is the HIUV zero bus bar interconnection film that we produce. It has low fluidity, avoids displacement of welding tape during metallization binding, thermal dimensional stability, high and low temperature resistance with no desoldering, shadow-free EL, high viscosity forms an effective bond between welding, tape, and cells. Next one, please. So this shows the high UV skin film shows no change in electrical contacts after high and low temperature cycling TC200. We'll go on the last one, Michael, which is about, I'll just brief on the different kind of matches that we have for the different products. This would be of interest to the viewers. Are we on the last slide, Michael?
Yes.
Okay. So, many questions come to us that what combination should be used. So, I'll just brief. In PERC, we suggest the EVA white EVA, N-type TOPCon, EPA white EVA, HJT, EP white EVA, for BC cells, EP white EVA, and for N-type BC, EP white EVA. I guess with this, I'll sign off. And if there's any other question or anything else, I'm happy to take it, please.
Okay. Thanks, Jitin. Great showing all these details. So maybe one question, because now you also showed the different options for the different cell technology approaches. So just to summarize, because the focus is mostly on TOPCon here, what
Yes.
is the most optimal encapsulant combination you are suggesting?
It's an excellent question, Michael. So, when it comes to TOPCon technology, selecting the right encapsulant combination depends on two main factors. A, the production cost. B, the quality and efficiency. From a cost efficiency perspective, EVA is a well-established and affordable option. It's widely used due to its cost effectiveness in production. On the other hand, if we focus on improving quality and performance, POE encapsulants become the top choice due to their superior durability and performance, especially in high-efficiency solar cell technologies like TOPCon. So considering both cost and performance, we believe the optimal solution is a combination of EPE and EVA. This combination will offer a balanced approach, providing enhanced durability while maintaining the cost efficiency, making it a great encapsulation solution for TOPCon. However, no matter the encapsulant solution a module maker chooses, HIUV offers a range of products to meet the specific needs of our customers, ensuring that we can provide the best fit. Thank you. Thank you for this question, please.
Thanks, Jitin.